Hi guys, we are talking about a new type of graph today. When you thought graphing couldn't get more exciting, we are going to introduce a second type of graph. So before we talked about position time graphs, which kind of looks similar to this little example right here. Okay, this is a position time graph. So position time graphs tell us where something is at a certain point in time in its motion. Lucky for us, we have a different type of graph that tells us how fast something is moving at a particular point in time. So you can see I've included, this was actually a little GIF, but it's not moving right now, so it's very sad. But there are three types of graphs. These aren't the only two graphs that exist. There are even acceleration time graphs, but we're not going to talk about that in regular physics, so lucky you. But you can see these shapes of these graphs look pretty different. They tell us different pieces of information throughout the motion, so that would make sense that they're not shaped exactly the same. So I'm going to scooch this up a little bit. This is a spring, and normally it's moving, right? But this position time graph is maybe indicating that it is at its resting position. It's at its zero position. It's not super scrunched up. It's not super stretched out. It's at its perfectly resting position. But it looks like it still has a velocity. And we can tell because this little line right here would be where velocity equals 0. So rest is actually just a point on a velocity time graph, and it wouldn't look like a flat line. Don't worry if you don't get that immediately. We are going to do some practice to get that down. So also this picture got larger, so you can't see what's on this PowerPoint, but you have access to my PowerPoint. But it just said position time graphs tell us where something is throughout a frame. Velocity time graphs tell us how fast something is moving throughout a time frame. Why do we have so many different graphs? Well, the slope of this type of graph, slope of that type of graph tells me velocity, right? So the slope of this type of graph would tell me something different. We're going to talk about what that tells me next. So things to remember, velocity is always on the y-axis. So time in both of these types of graphs and position time graphs, you remember time was always on the x-axis. Well, that's going to be true for the velocity time graphs. Time is always on the x-axis. But we have two different shapes of velocity time graphs down here. So we have velocity time and velocity time. Why these look different? 0 for the y-axis is right there in the middle, and positive above it and negative and below it. I could definitely have a negative velocity or a positive velocity. That's just telling me direction. And 0 is where I'm at rest, everywhere on that x-axis. I will never use this side of the graph because that would be where time is negative, and that's bad. We're never going to use that in physics. So that's why we only use the one side of the graph. The slope here, I kind of gave it away, tells me acceleration. So remember, your slope formula is y2 minus y1 over x2 minus x1. If my y in this case is velocity, so it'll be like velocity 1 minus velocity 2 or final minus initial over my change in time, that is literally my equation for acceleration. So that is kind of why we use a velocity time graph. It is very hard to calculate the acceleration on a position versus time graph without using calculus. We don't want to use that, okay? But we can find the slope of a velocity time graph and find acceleration from that very easily. So we can see different things from different points of view. It's kind of a good way to think of it. Excellent, so you should have space to fill in these examples in your notes. I'm only going to do the first two, so don't worry if you can't see the bottom one yet. But we have a position time graph over here off to the top left. And then we want to draw the corresponding velocity time graph off to the right. So before you try to translate it on your own, I want you to just focus on writing down what you definitely know about the first graph. What kind of velocity does it have? Positive or negative, or is it not moving? Well, on a position time graph, if it were flat, that would mean it's not moving. But it's definitely moving here, so we know definitely has a velocity, and I'm going to say it's a positive velocity. It's a positive velocity because it's a positive slope, and it looks like that slope is the same the whole way through. So I'm going to say the velocity is constant, which means I am not accelerating. So how that's going to look on a velocity time graph is whatever speed I would technically have to calculate the slope of this line. But whatever that slope is, it kind of looks like it's just 2. I would draw a straight flat line at whatever value my velocity is the entire time. Maybe it's 2. So that's why I drew it there. Great. So now this guy. This guy's curvy looking. And a lot of you would tell me this guy is slowing down. That's not exactly accurate. So please don't assume that. I definitely know it's a negative velocity because it's sloping down. Okay, if you look from left to right, it moves down. So definitely a negative velocity. And it's definitely accelerating. Here's a trick for how I can tell if it's accelerating on a position time graph. Anytime it's curvy, anytime it has a curve, it will definitely be accelerating. How can we tell what type of acceleration it is? Tricky. I'll have another slide where I can show you a trick to this. But for now, let's look at the shape of this graph. It starts off pretty flat. And on a flat line on a position time graph indicates it's at rest, it's not moving. But then as we move, it's getting steeper and steeper and steeper, which actually means it's getting faster, even though it looks like it's going down and hitting the ground. So it's speeding up, and maybe you remember from the other notes video, what direction do velocity and acceleration have to be in compared to each other for an object to speed up? They have to be in the same direction, so negative. So how I draw that on a velocity time graph. Remember, it's a negative velocity to start, and negative velocity will be below the x-axis. But how I would draw that on here is, so I'm definitely going to draw it on this side of the graph, the bottom side of the graph, because it's a negative velocity. And then on a velocity time graph, the slope is how I show acceleration. So since I have a negative acceleration, I'm going to have a negative slope. So that's going to look something like this. And you can kind of see it says the same information, it just looks different. It starts at rest, it starts not moving, just like it did over here, and then the velocity is actually getting bigger, further away from 0, just in the negative direction. Cool. Moving on to the last example, and then I might give you, if we have time, I'll give you a little trick for how to remember some of this stuff. So we have a funky looking graph that's split into segments. The first thing I notice is there is no curve. So we are going to have no acceleration in this graph. And I'm just going to break it into pieces. So let's look at that first part. Part A, positive velocity. Part B, flat, velocity is 0. Part C, positive velocity again. Part D, at rest again. Part E, it's sloping down, so I have a negative velocity. Now I'm going to try to draw that same thing on a velocity time graph. Again, to figure out where to draw it, like how high or how low, I should calculate the slope. And I can kind of do that really quickly. It's 4 divided by 2, my velocity would end up being, and then technically to do slope, you know how to do slope, I'm not going to spend time doing it now. My velocity there is 2 meters per second, and it's positive, and I'm doing that for 2 whole seconds. Great. For the next, I'm at 0. Some people like to just skip like that. Some people like to connect with a dotted line. Some people just like to draw a solid line. It's not important how you draw it. If you want to draw a continuous line, you can draw dots like that to separate it. That's totally fine. The next segment, it's going faster. It jumps up 4 spaces, 4 meters in a 1 second time frame. So that velocity is actually 4, and they only do it for, oops, I need to draw this one a little longer because he was at rest until 5 seconds, and he was only going 4 meters per second for 1 whole second until he got to 6. Dotted line, no dotted line, doesn't really matter. Great. For part D, From 6 to 8 seconds, he was at rest, so I'm going to drop down to 0 because when my velocity is 0, that means I'm at rest, right? And then for E, I have a negative velocity. And if I want to spend the time to calculate that, I can. He goes from 8 to 2, so he moves 6 in 2 seconds. So he has a -3 velocity. So my graph would look something like that. Not the prettiest of graphs, but there you have it. Some of you may have been frustrated as to why that looks the way it does. You have a blank space in your follow along notes, so if you would like, you can follow along with what I'm about to show you right now. It's just a dumb, silly little trick on another way to interpret the shapes of graphs and what they look like. So I'm going to start by drawing a position time graph. I'm going to draw a top and a bottom so I have lots of space to write what I want. Okay. Shoot, is there any way for me to shift that over? I'm going to cheat. Ooh, no, we're not. Just so my head's not in the way. Ooh, look at that. Look how smart I can be sometimes. All right. So I'm going to start off by drawing a positive velocity line. That's just a constant positive velocity line. And then I'm going to have a negative velocity line. Both of these could be switched. They could be on top or bottom of this graph. I'm just trying to fit all the things I want to show you on here, so this is just a way to space them out. Now I'm going to draw all the scary looking curves you can see on a graph. There's one. I'm going to draw that better. Oh, nope, still can't draw it. Something like that. Something like that. And yes, the sound effects help me. You could see any of these curves on top or bottom of the graph. The shape is the most important thing here. So I want you to start by looking at the top. All three of those lines have something in common with each other, and it's the fact that they're all positive velocity graph lines. Okay? They are all moving up, even if some of them are moving up faster than the other ones. The difference is these two pink lines, or purple lines, whatever you want to call that, they are curvy. So I know that means they are accelerating. Their slope is changing, which means their velocity is changing, which means they are accelerating. This one has no acceleration because there's no change in that slope. So now, how to figure out what kind of acceleration it is. Is this top line, is it speeding up or slowing down? It's definitely getting faster because that line is getting steeper. That means I'm moving more of a distance in a shorter amount of time. So it's speeding up, which means this must have a positive acceleration. I need those signs to be the same. This line is getting flatter, which means it's approaching rest. Flatter it is, the closer to rest it is, which means it's slowing down, which means these signs need to be opposite. I also have a dumb way to remember it. Do you want to hear it? It's pretty cute. In the other video I did over constant acceleration, I explained that accelerations are caused by forces, and they're directly related to forces. So whatever direction the force is in, that's the direction of the acceleration. So when I use my highlighter now, a different color, this curvy line looks kind of like my base positive velocity line, but it looks like someone pulled on that line. It looks like someone pulled it up in the positive direction. So a positive pull, meaning a positive acceleration. That flatter line looks just like this positive velocity baseline, but it looks like someone smushed it in the negative direction. So it received a force or a push in that negative direction. So that's my cute way. If you like it, use it. If you don't, don't. So now we're going to do the same thing on the bottom. You might have guessed it. All three of these lines are examples of negative velocities because they're all trending down. Okay, slope all going down. But the other two lines are curvy, so we know they are definitely accelerating versus this one does not. This line right here is getting steeper and steeper and steeper, which means it's speeding up, getting faster, meaning these signs have to be the same. getting faster in the negative direction. It's moving in the negative direction and getting pulled in that negative direction as well. So super speeding up. Versus this line is also getting flatter. Approaching rest. So this must have a sign opposite of my velocity, so a positive acceleration. Also my stupid thing, this top line right here looks just like a negative velocity line if I pulled it this way in the positive direction. So it's a negative velocity being pulled positively or negatively in this case. Cute. If you like it, use it. If you don't, don't. Ask your teacher if you have any more questions about graphing. Lots of practice will help with this.